In this video, we're going to write super fast Javafied code for our units to find their closest target. It will be super fast, which will enable us to have thousands of units looking for targets all at the same time. Let's begin! Hello and welcome, I'm your Code Monkey, and this channel is all about helping you learn how to make your own games with in-depth tutorials made by a professional indie game developer. So if you find the video helpful, consider subscribing. This video is a continuation of the previous video where we built units and targets and created systems for those units to find and destroy those targets. Now in that video we did everything using only ECS. And in this video we're going to use ECS combined with the job system in order to achieve maximum performance. So if you haven't already, check out that video first to see how the basic setup is done and how we're looking for the closest target using normal ECS systems. So let's see the scene in action. Here it is, and as you can see we have targets and units, and our units are actively looking for the closest target, they move towards it and they destroy them. Okay, so let's review the code to see how all of this works. So here is our basic starting script. And in here we have two functions, one to spawn a unit entity and another one to spawn a target entity. You can see here the entity archetype, they are very similar. The only difference is the tag component. So this one has a unit tag and this one has a target tag. Those tags are defined down here. As you can see, they are just empty components. Then we have our find target system. First, we cycle through all the entities that do not have the hasTarget component, but do have the unit component, so all the units without a target. We cycle through all of them, and then we cycle through all the target entities. We calculate which one is the closest, and if we do find a closest, then we add the component hasTarget using our closest target entity. Then finally, we have this system which runs on entities that do have the hasTarget component. It simply moves him towards the target, and once he gets within a certain distance, we simply destroy our target entity and remove the hasTarget component. Okay, so this whole thing is working perfectly fine, as you saw. Here we have our units, all of them actively looking for the closest target, move towards it and destroy it. Okay. However, right now we're not taking advantage of all the benefits that the entire Unity.stack provides. Here in our find target system, we're cycling through all the entities one by one just on the main thread. So for each unit we add, this system will get exponentially hard to run. So in order to make our code multi-threaded, all we need to do is convert this from a component system into a job component system. So let's go down here to make that. Let's call this a find target job system, and we're going to extend job component system. So in here we're going to do pretty much the same logic that we were doing previously, except we're going to do it inside a job. So we're going to have a job cycling through each unit, and in there we're going to search for the closest target. So let's start off by making our job. So we make here a struct for our find target job, and we implement iJob for each with entity, and we also want to grab the translation component. So in order to implement the iJob, we need to add the execute function. So with our definition here, it means that our execute method receives an entity, the index for that entity, and our translation component. Now for the translation, we don't want to modify it, so in here we can add the read-only attribute. Now we want our job to run only on our units. Right now, this job would be working on every single entity that contains a translation component. So in order to limit where our job runs, you can go here in order to add the attribute, and we're going to add the require component tag type of unit. So now the job will only run on entities that contain the unit tag. And then we also want to ignore the units that already have a target, so we can use the attribute exclude component, pass in the type of hasTarget. Okay, so now our job is clearly defined to work solely on units without a target. So here we essentially have the exact same filters that we have in here, working on the units with none hasTarget with all unit and doing it for each. That's exactly the same thing we're doing in here. Now inside, in order to look for the closest target, we need to know a list of all of our targets. So that means in here we need a native array to hold all of our targets, so an entity for our target array. However, in order to identify the closest target, we don't just need the entity, but we also need the position. So we could either have two arrays in here, one for the entity and one for the position, or we can just go up here to define a simple struct to hold both the entity and the position. So in here we make a simple struct, let's call it entity with position. And in here we're going to have an entity field and a float3 for the position. Alright, so now in our job we receive this instead. So essentially we're receiving an array of entities with their position. We also don't want to modify this array, so we can add the read-only attribute. And since this native array won't be running inside our job, which is managed by our job system, we want to make sure the array gets disposed correctly, so we can add the attribute deallocate on job completion, which means the job system will automatically deallocate this array when it goes through and completes the job. So here we have all the information that the job needs. We have all our targets and their positions. And now inside our job, the logic we're going to do is pretty much exactly the same thing we were doing previously. So let's copy this code and see what we need to change. So for the unit position, it's the translation.value. Then instead of cycling through the entities, we cycle through our array. So we cycle through all of our target entities. Then here, if the closest is null, then this is the first one we found, so we set this one, very simple. And if not, we check which one is closest. So if this one dot position is closer than the current closest, then this one becomes the new closest. So that's pretty much the exact same logic for looking for the closest within our target list. And then if we do have the closest target entity, we want to add the hasTarget component. However, inside a job, we cannot use the static variable for our post-update commands, but instead we can pass in a field that will contain an entity command buffer. So in here, a public entity command buffer. Let's call it entity command buffer. A command buffer essentially holds the commands that will be executed at a later time. And in order to write it concurrently on our job, we need to use the command buffer.concurrent. Okay, so now we can go in here to call our add component function. Takes a job index, so we can use the entity index, then our entity, and then our hasTarget component. Okay, so here we have our job doing exactly the same thing that we were doing previously on a normal component system, except right now we have our job component system. So with the job defined, now we need to actually create it, schedule it, and complete it. So down here on the onUpdate function, first we need to create an instance of our job. And now in here we need to pass in our target array, so we need to create it before that. Now here we need to know the size of our array, which means we need to know how many targets are on the scene. So in order to cycle through all of our targets, we need to create an entity query containing all the target entities. So we create an entity query for the target query, and we get the entity query. And it's in here that we pass in our parameters. So in this case, we want our targets. So type of target. Then we also want with the translation component. However, we only wanted read only, so we can use the component type dot read only of type translation. So we have our target query, which is essentially asking the entity manager to give us all the entities that contain a target and a read only translation component. Then we can grab all the entities that match this query and put them into a native array of entities for the target entity array. And it will simply be the target query dot toEntity array. Okay, so we now have an array containing all of our target entities. Now we also need containing all of our target translations. So for that, we use toComponentDataArray with our translation components and using the same allocator. And now in here on our target array, we can spawn it using the length of our target entity array. Okay, so we do a query to get all the entities with target and translation. Then we get an array containing all of those entities, another array containing all translation of those entities. And then we create a new entity with position array that we're now going to have to fill. So all we need is to cycle through it. And we set the target array on that index to be a new entity with position. And we're going to pass in the entity as our target entity array of the same index, and our position as our target translation array of the same index dot value. And actually here we have an error, since this should be a float 3 for the position so that it holds the x, y, and z. Okay. So here we have correctly filled up our target array containing entities with position, which contains the entity and the position of all of our targets. So now we can simply pass into our job. Now in here, since we are working with native arrays, we have to make sure to dispose of them. Our target array gets disposed after the job executes, so we don't have to worry about that one, but we do need to dispose these two. So in here .dispose, and do the same thing for the other one, for target translation. Okay. So we have prepared all the data that the job needs. Now the last thing that the job needs is the entity command buffer. So here we need to pass in the command buffer that runs after the update. So previously we were using up here the post update commands. However, this one only exists on the normal component system and not on the job component system. So we need to use something different. So let's protected overwrite our onCreate function. And in here, we're going to go into the world to get or create a system. In this case, let's grab the end simulation entity command buffer system. And let's store this. So we have this command buffer system, which runs after the main simulation. So this is perfect to use as our entity command buffer. So we simply go in here, we pass it to the job and create a command buffer. And since we want to write it concurrently on the job, we need to pass in to concurrent. So just like that, our job will now be able to run our line in order to add a component at the end of the frame. And the last thing we need is to tell the entity command buffer system to run our commands after the job has happened. So in order to do that, first we schedule our job. So find target job, and we call schedule. We schedule this job. This returns our job handle. And then we tell the command buffer system to add the job handle for producer, and we pass in the job handle. Essentially, this tells it to execute the command buffer after the job has been completed. And finally, on the job component system, we need to return the job handle from the onUpdate. So after this, we just do a return on our job handle. All right, so this might seem like a lot of code, but it's actually very simple, and you will see what benefits we get from writing it this way. So first, up here, we define our specific job. This job will run on our unit entities. Over here, we receive an array containing the entity and position of all of our targets. Then for each unit entity, we cycle through the targets and calculate the closest. If we do find the closest, we add the component. And down here, all we need to do is prepare the data that the job will work on. So we grab all of our targets, we grab the entity and the translation, we create our specific struct, we pass it to the job, we'll let the job system schedule it to do its thing, and afterwards we have the command buffer executing. Alright, so let's test, and we should be able to see everything still the same. In order to disable, let's go up here and comment out our previous component system in order to make sure it doesn't run. Okay, so let's see. And yep, here we have our units. They are still being spawned, they are still finding the closest target, moving towards it and destroying it. Okay, so our logic is still working the same. Now let's see exactly how much faster this method is compared to the previous one. So in here, in order to test out how much time this is taking, let's stop adding the component. So this way they won't continually search for targets every single frame. And let's also test out the previous code. So let's instead use the component system and comment out the job component system. Let's see how long the normal component system takes. And in here, instead of just 5 targets, let's spawn 1,000 units and 1,000 targets. And we stop spawning. Okay. So we have a nice test with 1,000 units looking for 1,000 targets, and it's currently running on a normal component system. Okay, so here we have 1,000 units looking through 1,000 targets, and as you can see, the performance is pretty bad. We have the CPU taking 260 milliseconds, and the game is running at 4 frames per second. None of them are moving since we're not actually adding the hasTarget component, so all we're testing is really how long it takes to find a target. So again, remember, this is a normal component system. So essentially for every single one of those 1,000 units, it's doing a cycle on a single thread, and for every single one of those 1,000, it's cycling through another 1,000 times for every single target. So you can already see this is a lot of single-threaded sequential work. So we can, for example, inspect with the profiler. And here's our profiler, and as you can see, about 250 milliseconds. Okay, so this is the normal one. Now let's see the improvement with our job system. So here we comment out the normal component system, and now we try out the job component system. Okay, let's test. And here we are, and as you can see, already a massive improvement. We went from 250 milliseconds per frame down to 70 milliseconds per frame, and from 4 frames per second to 14 frames per second. And here in the profiler, you can see it taking 70 milliseconds, and all our jobs are being quite busy. Now, if you've seen my other videos on ECS and the job system, you know burst can provide an insane boost. So let's try adding it to this job. In order to add burst, all we need is to add burst compile in here, which is using unity.burst. Okay, that's all it takes to add burst. So let's go back. Okay, so here we are, and again, using the normal component system, we were taking 250 milliseconds. Using the job component system, we are taking 70 milliseconds. And now let's enable burst. And there you go, from 70 down to 2 milliseconds. We can open up the profiler and take a look. And there you go, the whole simulation taking 0.6 milliseconds. And the find target job system taking just 0.3 milliseconds. So as you can see, that's pretty insane performance. So let's re-enable our add hasTarget component. So in here we just go and put this back. So we should now have our units find target and destroy them. And as soon as we try, we come up with a bunch of errors. So all of these errors are essentially saying that we cannot use burst and use the entity command buffer at the same time. The reason why burst is so fast is because it works on an extremely limited subset of C#, and in that we have a bunch of limitations. So in this case, we cannot use the entity command buffer in order to add a new hasTarget component. So that's pretty bad, but we can work around that. So here on our find target job, essentially the only thing we cannot use burst for is this one right here at the end. So that means that we can essentially split this job into two and have one job to calculate the closest entity and another job to actually add the hasTarget component. So we will have one using burst and one not. Okay, so let's do that. Let's copy this job. Let's call it the find target burst job. And again, in here we cannot use the entity command, so we get rid of this. So all we're doing is cycling through our targets and finding the closest. However, then we need to know which one is closest, so on another job we can actually add it. So in order to store the closest, let's also go up here into add a public native array of type entity, and this will be the closest target entity array. So we do all of our calculations, and then we put our closest on the same index. So we put the closest target entity in there. So we have this native array that we are using in this job, essentially using as our output. So down here, when we make our find target burst job, for the target array, we use the same one, and then instead of passing in the entity command buffer, we need to pass in an empty array the size of our units. So we need a native array of entities. And just like up here, let's call it the closest target entity array. Now in here, we need to know the length. So for the length, let's do the same thing we did in here. We grab a entity query, except this is the unit query, and we get it with type of unit. And here, instead of using the component type read only, let's use the exclude of type has target, since we only want the units that do not have a target. Then here we know our length. In order to go here, calculate the length, and that's the size of our array. All right, so we have our closest target entity array, and we pass this one into the job. So this job has burst enabled, and it locates the closest target and puts the result on this array. And then we make another job Let's make here a private struct. Let's call it the add component job. And it will be very similar. We also use the iJob for each with entity, and let's receive a translation. And in here we get a entity command buffer dot concurrent for our entity command buffer. And we're also going to receive a native array of type entity for our closest target entity array. We can add the same attributes that we added in here. So this one will be read-only and it will deallocate on the job completion. And here all we do is we test if the closest target entity array of this index is not entity.no. So if this entity has a closest target, then we simply go into the entity command buffer in order to add the component using this index into this entity, a new has target component with the target entity as our closest target entity in this index. And that's it. This is our second job, which is only responsible for adding the component to the entities that do have a target. And we have our first job, which uses burst and just calculates the closest. So this way we get the best of both worlds. We use burst for maximum performance and we still have our behavior working. So now we need to actually schedule this job. So down here, let's make a add component job. For the closest target entity array, we use the one that came out of that job. For the entity command buffer, we pass in the same we were using previously. And now we schedule this job. So the add component job.schedule. And now in here we schedule it with a dependency of our first job, since first we want to find the closest and then we add the component. So we run this job, and when this job completes, we run the second job. And that's it. This way we can benefit from burst in order to do all the find closest math, and then we have a separate job to do the part that burst cannot do. So let's test and see if everything is working. And run, and yep, here we are, and they all automatically found the closest, moved to it, and completely destroyed all of the targets. So again, let's check out the performance difference for all of our different methods. So here, let's just disable adding the component so we can test. So first, let's try out just the component system. So here we have just the component system looking for targets. We have 1,000 units and 1,000 targets taking 270 milliseconds. Okay. Now here we are using the job component system, and we went from 270 down to 70 milliseconds. So a massive improvement. And now finally we enable burst. And there you go, down from 70 all the way down to 2.5 milliseconds. Again, we have 1,000 units looking through 1,000 targets. All of that happening every single frame, and yet we have 2.5 milliseconds. So you can see the massive benefit you get when you use the entire .stack. As always, you can download the project files and utilities from unitycodemonkey.com. If you liked the video, subscribe to the channel for more Unity tutorials. Post any questions you have in the comments and I'll do my best to answer them. Alright, see you next time.